All right, good afternoon, everybody. Let's get started. So let's continue on talking about electronic sensors. And so we're going to move on to thermocouples. You can use the semiconductor-based devices, silicon-based devices, and the thermistors for measurements in the range of, room temperature up to maybe 200 or 300 degrees, depends on the part. But if you really need to measure very high temperatures, like temperatures of, I use exhaust gas as an example, but a combustion chamber, something that's in the, above a few hundred degrees, maybe into the 1,000, 2,000 degree level, then you need to use thermocouples. So I think it's worth covering how these work, and then probably more importantly, well, how do you use them? So here's how thermocouples work. Let's suppose you have a metal wire. So this is a wire here, and it's metal A, and we'll talk about what kinds of metals you can use. But metal A, if it's just sitting there at room temperature, it's a uniform temperature from end to end. And if you measured the voltage, you would find that you have, surprise, surprise, 0 volts from one end to the other across this conductor. But if you take that metal and you heat one end, what's going to happen is you're going to excite these electrons on the left where the flame is, and those electrons are going to tend to be less dense on the left as they spread out due to the temperature and become more dense on the right. So you have a non-uniform charge distribution now in this metal. And if you have a non-uniform charge distribution like this, you're going to have a voltage. Okay, so there are fewer electrons on the left, denser electrons on the right. So you're going to get a voltage that's greater than 0. Let's call this V sub A for metal A. So this effect of causing a voltage across this conductor is called the Seebeck effect. So we're going to use the Seebeck effect. As you can tell, we can change voltages with temperature. So we're going to use the Seebeck effect to measure temperature. Okay, so now let's take another metal, a different type of metal, metal B. And we're going to do the same thing. We're going to heat up one end and leave the other end cold, right? And so in this case, you'll get the same response. You will have a voltage VB across metal B, positive on the left where you have lower density of electrons, negative on the right where you have a higher density. Okay, but since these are two different metals, those voltages can be different. Okay, metals respond differently. Different metals respond differently. And so let's suppose that we have chosen metals such that metal B, when you heat up metal A and metal B at the left side, the same temperature, right? VB would be greater than VA. So we can do something with this. What we're going to do is we're going to join two ends together, the left side of metal A, the left side of metal B, and maybe we'll weld those together. You can actually just twist these metals together. I've done that too, and you'll form a thermocouple. So that left side, that's called generally the hot junction. Usually you're measuring something hot over there. And the hot junction is going to be defined to have the temperature T sub Tc, the thermocouple temperature. On the other side, where it's cold, we'll call that the cold junction. Okay, and that's going to have the temperature T sub Cj for cold junction. And now, so we've induced these voltages, not induced, but we've caused these voltages to happen because of the Seebeck effect across each one of those metals. And remember, metal A and metal B have different voltages from end to end. So we're going to get this voltage across the cold junction. And so if you've ever bought a multimeter or used a thermocouple on a data acquisition device, you've probably seen thermocouples that look like this. They have some kind of connector on this on the right here, as shown. And then right at the end here, you can kind of see it. It's two wires welded together, and that's the hot junction. So that's where you would measure the temperature. And on the right, that's where you plug it into the voltmeter. So the thermocouple voltage VTC on the right here, it increases as the difference between the hot junction and the cold junction increases. Okay, you can see that as you heat the left side on the left figure here, VB is going to increase greater than VA, so VTC is going to be a positive value, an increase with increasing temperature. So the hot junction temperature is the unknown voltage to be measured. And the cold junction temperature, I say, is known, but it really needs to be known. So what you'll see in integrated circuits that are designed to take the input from a thermocouple, they have usually temperature compensation, some temperature sensor in them to compensate for the cold junction temperature, because this thermocouple is going to give you the difference in temperature between the hot junction and the cold junction. So you need the cold junction temperature and then compensate for that, so you know the real temperature of the hot junction, not just the difference between hot and cold. Okay, so then you're going to use a relationship between the thermocouple temperature, the hot junction temperature, and the thermocouple voltage all the way on the right at the cold junction to determine the thermocouple temperature, right, and compensate for the cold junction. Okay, so that's the principle behind how thermocouples work. They use the Seebeck effect. You get two different voltages across two different metal types. You connect them at the hot junction, and then we're going to do something at the cold junction to measure and compensate. All right. So let's talk about how to use them. So let's talk about relating the temperature difference, the hot junction versus the cold junction, to the thermocouple voltage. So if you go into data sheets, and I'll actually give you a link to a website where you can look at the different types of thermocouples and the different types of metals, and the temperature ranges they're designed for, and then the voltage difference across their entire range, and then the Seebeck coefficient. So thermocouples use the different pairs of metal wires just to because of different temperature ranges and different temperature sensitivities, right? You can see that type T here only goes minus 200 to plus 400, and type K goes all the way up to 1370. And so these different metal pairs are given letters to designate their type. And you choose the type based on your application, your temperature range, the sensitivity you have, maybe the amplifier that you have to amplify the thermocouple voltage. And type K is a really common one. Honestly, I don't really know why, but it has a pretty good range, and you'll find them anywhere. If you've bought a multimeter that came with a temperature measurement capability, it usually comes with a temperature probe that is a thermocouple, and it's usually a type K thermocouple. So you can measure from minus 270 C, really cold, to plus 1370. And actually type K, I know for a fact type K can go higher than that, because I measure temperatures above 15. Oh, no, I'm sorry. I measure temperatures above 1500 Fahrenheit, and this is Celsius. So I take that back. And you can go to a NIST website that publishes tables and equations to describe voltage versus temperature. And so you can go to this website. It's on the printed slides or the PDF slides if you want to check out how that's specified. All right. So let's take a look at this. Well, before I go to a plot, look at this Seebeck coefficient. That's really small, microvolts per degree C. And that implies you have some linear characteristic, because you're given a slope here, but you're given it at a specific temperature. which implies looking to the future that you're probably going to have some nonlinearities there. But look at how small that that coefficient is in microvolts per degree C, and then look at the total range over the temperature range. The range of voltage, we're talking millivolts here. Right? So if we plot this, you can see that yes, indeed, there's a very small change in millivolts over the wide temperature range. So look at type K, the gray line here. It's common. So at 0, so if you have a cold junction at 0 degrees C and a hot junction at 0 degrees C, for all of these, you're going to get 0 volts, right? This is thermocouple voltage on the left and temperature of the hot junction on the horizontal axis here. Okay, so this is all reference to 0 degrees C. So as you increase the temperature, the voltage of the thermocouple goes up, and it's sort of linear, right? It's not so linear down at the cold end, but that kind of looks linear there. But imagine if you're measuring a temperature between, 0 degrees C and 100 degrees C. You could see that you're only changing a few millivolts in there at the cold junction end. Okay, so that means that you're really going to need an amplifier to amplify the voltage just to make it usable. Remember, in the beginning of talking about sensors, I say many of these sensors output a voltage, and I call it almost unusable, right? Because you can't directly measure it. You need some kind of interface circuit to condition that voltage, to amplify it or filter it or even attenuate it so that you can use it with a analog to digital converter. You know the ranges now for those and the resolution, or just a voltmeter. And also to minimize the effect of noise, because having a few microvolts of noise on a wire is not uncommon. So, you could have a very noisy measurement if you don't have some kind of interface circuit, right? So imagine you have maybe a thermocouple here, and you need to amplify it. There are integrated circuits that do this for you. You can build a circuit. You could use an op amp and build a circuit and filter it. But there are dedicated circuits out there that do this. So here's an example of, this is a Maxim part. It's an IC that is intended to make temperature measurements using different types of thermocouples, and you actually have to specify what thermocouple type you're using. So it has an amplifier built in. So here are the inputs, right, coming from the cold junction. That goes right into an amplifier. And when switch S4 is closed, that goes to an analog to digital converter to sample that voltage. All right. And then, that gives you the temperature difference between the hot end, the tip of the thermocouple here, and the cold side, the cold junction. But it doesn't offset for the temperature at the cold junction. Well, that's what this chip is meant to do. There's internal temperature compensation. So it has a sensor built in, probably one of those silicon-based temperature sensors. And this ADC switches between the amplifier output from the thermocouple and the internal temperature sensor so that the ADC can compensate. Okay, so then this IC outputs in a digital format. So you have this digital control is probably more than just control, but calculation. And it outputs in serial data over a SPI bus, the temperature data. Okay, so this is a pretty easy way to use a thermocouple. You don't have to worry that the signal is going to be too small to sense with an ADC, because this chip has an ADC built in. And then what you would do is you would connect a microcontroller, a digital port of a microcontroller, to get the data via a serial peripheral interface, the SPI bus. All right. Okay. Then let's try a clicker problem. So grab your clicker apps and let's have you calculate a voltage for a thermocouple. So suppose you're considering using a type K thermocouple to measure an engine's exhaust gas temperature, so really high temperature. That's why you're using a thermocouple. Okay, so you want to measure this voltage at the cold junction. And using a rough linear approximation, type K thermocouples produce a voltage that changes as 40 microvolts per degree C. Right? So if you want to get that more accurate, you can use the 38.9 something. If you really want to get accurate, you could use a table lookup or a polynomial equation. And so the maximum exhaust gas temperature is approximately 1500 F, and that would be 815 C. And the cold junction of the thermocouple is at room temperature. So you have remember, you're measuring the temperature difference here between the hot junction and the cold junction in C if you're using this 40 microvolts per degree C. So what voltage would you expect at the thermocouple's cold junction at its output? All right, let's talk about this. So this 40 microvolts per degree C applies to the difference in temperature between the hot junction and the cold junction. So the voltage you're going to see at the output is approximately 40 microvolts per degree C times the temperature difference. Okay, so we have 815 minus 21, about 32 millivolts. Okay, and I use this high temperature application because even though this temperature is very high, the temperature difference between the hot junction and the cold junction is very high. You still get a really small voltage, 32 millivolts. And so to measure that would be challenging directly without some kind of amplifier. And so measurements of this voltage directly with an ADC would result in poor temperature resolution. So, in lab, you're using an ADC with a full scale range set to 1.1 volts, and it's a 10-bit ADC. So that's, I think we said 1.1 millivolts per quantization level, right? So if you apply this 40 microvolts per degree C, if my calculation is right, the temperature resolution, if you just sampled the thermocouple output directly, would be about 27 C per quantization level. So, it's a pretty big jump. It depends. Maybe that works, but probably not, especially at lower temperature differences. So you typically use a thermocouple amplifier IC. You can buy analog amplifiers that are meant for thermocouples and then sample that output voltage of the IC yourself with a microcontroller's ADC, or you can buy, like I showed you on the previous slide, an integrated circuit with an amplifier and ADC altogether. All right, any questions on that?
Is there ever a temperature range? Like if you know that your application will provide you a decent, I don't know, resolution, is there ever a situation in which you can directly measure with an ADC?
Yeah, any ADC that I've ever used has had the range of maybe 1 volt, I think down to maybe a quarter volt, but not much smaller than that. So I can't think of a situation. Well, if you're measuring a big temperature range like 0 to 800 degrees C, and you can deal with a resolution of 25 or 50 degrees C, then you probably could, right? You could use the ADC and
If
directly
you just
connect it.
treated it like a switch, maybe in the programming, like if you just needed something that was above, say, 800, if you knew that it was above, then some code process, then it would be useful. But
Yeah,
otherwise, if you need
actually,
resolution,
that's a good
it's kind of like,
example. And like if you needed, like if you go above 800 and you didn't care if it was like, 750 to 850, right? If you didn't care about
yeah,
that,
yeah, yeah.
then yeah,
Okay.
you could do that. It would save you a few bucks on your product. It
Okay.
would, because these amplifiers, I forget, I've bought them before, and they might be a couple bucks.
Okay.
They're not as cheap as op amps, but Still not super expensive.
Thanks.
All right. Okay, so let's suppose you need something with a little better accuracy, although these are pretty accurate. But if you need just a little better accuracy and you can tolerate a smaller temperature swing, bigger than a silicon-based temperature sensor, a bigger range than that, but smaller than a thermocouple, you could use a resistance temperature detector. Okay, so this is an RTD down here. So RTDs use a wire, and it's a wire with a known resistance versus temperature characteristic. So you're basically just measuring, you're hoping for a wire that has a bad resistance tolerance. And that the wire that's often used, the metal that's often used is platinum because it has a stable temperature relationship. And so you'll see RTDs labeled as a type PT100. And so those sensors use a platinum wire, and they have 100 ohms resistance at 0 degrees C. And then that resistance changes based on temperature. And so this is the resistance change per degree C, 0.385 ohms per degree C. And there are different ways to build these up. So here's an example at the lower left here. But there are also other types, like this thin film sensor. So this thin film sensor has a substrate, so that gray block in this cartoon is a substrate. On the right, these are the leads in the cartoon. Here's a real device on the right here. This is a thin film RTD. And then metal is deposited on that substrate, and you see this kind of racetrack here, so that you get a longer wire for a bigger resistance change. And these are the least expensive and generally the most rugged, these types of RTD sensors. But there's a trade for everything. And these are considered to be the least stable RTD, okay? The least stable of these kinds of detectors. Another type is the coiled RTD sensor. So here's another cartoon of one. And these have a spiral wire, very thin spiral wire, put into this housing. And it's packed with ceramic powder. And so that allows the wire to expand with temperature, and it relieves the mechanical strain in there. So the wire won't break due to thermal stress, but these are generally not considered suitable for high vibration environments. And then there are wire wound RTD sensors. And that's a thin wire around a ceramic or glass mandrel. So like this. And this also, the coiling of the wire also allows the wire to expand and relieve strain. Okay, so there are these different types. They all work on this principle of a metal whose resistance changes predictably as temperature changes. So here's how to use them. So you use measured data, and it's usually in the form of a lookup table, or you can actually find equations that represent kind of the nonlinear characteristic of these. And you determine the temperature from the RTD resistance. So here's a plot out of a data sheet that shows the resistance from negative 200 C up to 700 C. So that's the range of this RTD detector. So it's not going up to the 1300 C of a thermocouple, but it's still got a pretty good range. And you can use a straight line approximation, especially for these lower temperatures, right? So these lower temperatures in the kind of the cooking oven range, it's pretty linear. And then that straight line approximation deviates from the real resistance as you get up to the higher temperatures. If you don't want to use the linear approximation, there's an equation for everything. So here is a polynomial equation that, again, it's a better approximation for the real RTD resistance. Okay, and here are your coefficients here. And I think this is for platinum. All right. So, but now that we have this resistance that starts out at 100 ohms at 0 degrees C and goes up to 350 ohms at 600-ish, we need some way to accurately measure very small changes in resistance, because if you're just changing just a few degrees, then you're not getting that much of a resistance change. And you'll see this is a common problem, especially when we get the strain gauges. So how do you do this? Okay, so there's a way to just directly use a resistance measuring circuit. So cause a current to happen, measure the voltage, a known current, and measure the resistance of the RTD. And so once you know V, you know I, then you can calculate the resistance between those two wires. Now, those wires, as you saw in lab, these wires have resistance. So this is the resistance of wire 1, this is the resistance of wire 2, and then you have this RTD here. And so really that measurement is approximately the resistance of the RTD. And then you'd go back over to this plot on the left or use the equation, figure out what the temperature is. That works for short wires, but if you have long wires, let's suppose you're instrumenting, you're like that SR-71, you wouldn't measure an SR-71 jet engine with this, but if you had some kind of engine that's 30 feet away and you're running it, you don't want to be close to it, and you have temperature detectors there and your digital analog to digital interface is 30 feet away, then you have long wires and that wire resistance is going to matter. So you can use the 4-wire connection. Okay, this is similar to in one of the first lectures, someone in this class had asked, well, what's the 2-wire versus 4-wire connection on our voltmeters, on our multimeters in lab? This is just like that principle. This is using 4 connections to a resistor to get a more accurate resistance measurement of that resistor. Okay, so here, let's suppose you have long wires. So these resistances RW1 and RW2, wire 1 and wire 2, they can be pretty big. And they can mess up your resistance measurement of the RTD. Okay, so they have non-negligible resistance. So what you can do is you can add 2 more wires. And you can measure the resistance like this. You use wires 3 and 4 for a voltage measurement, okay? And you use wires 1 and 2 to flow current. Okay, so you're going to have a voltage drop across wire 1 and across wire 2. But you'll know the current. The current's not going anywhere. The current is going through the RTD. Okay. But wire 3 and wire 4, they're connected to high impedance inputs to a voltmeter back here, or an ADC. And so there's very little current going through, and almost negligible current going through the wires 3 and 4. And so there's very little voltage drop, almost negligible, consider it negligible. So now you can get a very accurate voltage measurement right at the terminals of the RTD. And you can know the current going through that RTD, so you can calculate the resistance. Okay. And you could do this a couple ways. You could measure the voltage and current back here, or you can figure out the actual resistance of wire 1 and wire 2 based on your known current and your known voltages across those pairs. So a couple ways to do that. So that's the 4-wire connection. That's also the way you can use the voltmeter, the ohm meter in lab to measure resistance if your resistor is far away. There's also a 3-wire connection. And so you would only get the resistance of one of the wires. So it's a compromise. If you only have 3 wires that you can use, then you can use the 3-wire approach. All right, so let's talk about continuing how to use them. All right, so here is an RTD right here. You can see at the end of this, the coiled up wire, you have a probe. The other end, you have your wire connections there. And so you can buy, as expected, interface ICs to make a measurement with an RTD. And so this particular one, this is an Adafruit one that you can buy on a board as this chip that is designed for the Platinum, the PT100 RTD. Okay, it uses that Maxim chip. So you can plug that into your RTD and then connect a microcontroller, right? So the IC determines the resistance or a number proportional to the resistance, and it outputs a digital value that can be converted to temperature by you. And how would you do that? You do that with a microcontroller. So you connect, again, this looks like a SPI bus, serial data, both configuring this integrated circuit and reading temperature and other data out of the circuit. Okay. And then you can, let's see, this has a temperature calculation. The ADC value that you get out of this chip divided by 32 minus 256 is the temperature in degrees C. All right, so let's see, if you take a look at this chip, you'll see at the top, you have VDD, that's so we've been calling our supply voltages VCC. VCC is common when you have a circuit that is made of bipolar junction transistors. A lot of the collectors connect to the VCC. VEE is either ground or a negative voltage. Well, when you have a FET-based circuit or integrated circuit, oftentimes they'll use VDD instead of VCC. D stands for drain instead of C, collector. Okay, it's just nomenclature. So if you look on the right, here's the RTD, and it's using a 4-wire approach. So there's this force plus and force minus with the arrows here. So it looks like that the current is flowing through the force plus, out of the force plus, through the RTD, and then to the force minus. Okay. And then the RTD in plus and RTD in minus, that's the voltage measurement. And so you have very little current going through our cable of those two inner connections, because RTD in is probably a very high impedance input. So you don't get a big voltage drop or a very negligible voltage drop or zero voltage drop if there's no current across those two sense cables. And then there's a capacitor here. This capacitor is there for a filter, as a filter. All right. Okay, so here's a summary of the temperature sensors that we talked about. We have the semiconductor-based, a thermistor, a thermocouple, and an RTD. So here are all of the ranges of those sensors. So the semiconductor-based temperature sensor has the narrowest range. It's typically used on circuit boards to measure circuit board temperature. Maybe in thermostats, you can use them because that's within this range. You could not use this for an oven temperature sensor because it only goes up to about 300 F. And so, it's a relatively narrow range, but good for applications that are in a pretty benign environment. So then you can move up to thermistors, and thermistors have a wider temperature range. Okay. And then you still have to do some interfacing to that. And then move up to thermocouples, and that's really the widest range. So minus 300 F to 4200 F. So you really have a very wide temperature range to work with here. And if you want to step up accuracy just a little bit, you can move to RTDs. And so the range there is minus 300 to plus 1500. What I did to get these ranges, I looked at data sheets. So you look at lots of references and you will see a different range in in references. You know, how does an RTD work and what's its range? You'll find different articles and they have different ranges. So these are approximate ranges. And I tried to find the extremes that were credible, like finding data sheets and products that I could buy that would actually do this. So these are rough ranges, but it does give you an idea of, you know, if you have a really hot thing you have to measure, then use a thermocouple. And if you have a pretty benign environment and you want a digital interface, for example, you just use one of these semiconductor-based sensors. Okay, interface complexity. The silicon-based, the semiconductor-based, it's pretty simple. You can have an analog or a digital output of that. And there are libraries in the microcontroller that will help you with that. The thermistor, you can create a simple circuit with another resistor, get an analog output, sample it with an ADC, and do a conversion, right? Lookup table or an equation. Thermocouples, I call that moderate interface complexity because you have to have some kind of interface. You have to have some integrated circuit that's either just an amplifier or more likely an amplifier with a built-in ADC. And the same thing with the RTD. Because the resistance change is so small, well, you still need some kind of interface circuit. Okay, so typical accuracies. So you'll see rated accuracies of different products from 0.5 degree C to 5 degrees C. There's a thermistor. You'll see that they can be very accurate. Thermocouples, again, pretty accurate, and the RTDs claim to be kind of the best of both worlds between thermistors and thermocouples because they have a wider temperature range than thermistors and a better accuracy than thermocouples. And so response time, that's another critical thing, right? If you, if you've ever used an old analog thermometer to cook a steak versus an instant read thermometer, right? You know, there's a response time factor there that you care about. So these semiconductor-based temperature sensors, they can be 10 milliseconds. You know, they're sub 1 second response time to get to a temperature within their accuracy rating. Thermistors, they can be fast or they can be slow. It depends. Depends how they're packaged. Same thing for thermocouples. They can be fast, especially if you have the junction exposed, like this one right up here. That is the junction right up there. Sometimes the thermocouples are packed in a protective casing, and then so that makes their response a bit slower. And then RTDs, they have the slowest of all responses, and the corresponding trades there. And like I say, as always, it depends. So if you're looking for a temperature sensor for a given application that you have in mind, use these as general guidelines, and it's great to point you in a direction and then go find some examples, go get some data sheets and see what the manufacturer claims for their particular product. All right. So examples of applications, I already mentioned the circuit board over here on the left. Thermistors are sometimes used there. RTDs, I've seen these in smokers, in like grills and smokers. And for some reason, some of them like RTDs over thermocouples. Not sure why, but there must be some reason. Probably has to do with cost and response time and accuracy. Okay. All right, so looking at a given application, I just wanted to throw one of these out there. So why would you want to measure really hot temperatures? And this is an aircraft engine application where most general aviation piston engines, the higher performance ones, have temperature sensors in their exhaust. And that's because the pilot usually manually adjusts a mixture control to set the fuel to air ratio that goes into the cylinders from the intake manifold. And so what happens is if the mixture is too rich, meaning if you have too much fuel per air volume going in, then you get low power, you get fouled spark plugs, you get low fuel efficiency, high fuel burn. And if the mixture is too lean, the engine runs rough and it's low power. Um, and also the mixture must change with altitude, because as you go up, at sea level, you have about 30 inches of mercury pressure. I speak in inches of mercury. And then you go up to 14,000 feet and you have 16 inches. And so air density, air pressure changes, and you get this kind of characteristic here. So you change from rich to lean. And the point of this is that you're really monitoring. So pilots are really monitoring temperatures of the exhaust gas and temperatures of the cylinder heads, because these engines are designed to be really light. So they're a lot more fragile than car engines. And you can run either high power or high economy, depending upon what you're trying to achieve. But you can see right here, this is an exhaust pipe. You have the EGT probe, has a hose clamp on it. The thermocouple is actually out in the end here in the probe, and that EGT probe sits in the exhaust stream for hundreds of hours before they need replacement, and some of them go 2,000 hours. But think about that harsh environment, right? You're sitting there in this hot, corrosive environment, and so you wouldn't use a silicon-based temperature sensor there. You wouldn't use a thermistor there; it's too hot. And so thermocouples are chosen. And then there are these cylinder head temperature probes, one on each cylinder, and they tell you the temperature of the aluminum head of the cylinder. And so these have to tolerate high vibration and high temperature. So that's an example, right? If you're measuring, if you have some kind of combustion research going on and you have to measure flame, right? Some output of a combustion chamber, then you would probably use a thermocouple. All right, so that completes temperature sensors. And so these are the sensors that we're covering during these few lectures. So we cover temperature sensors. We're going to move on to light sensors next, and then cover the rest of these in the next few lectures. Okay, so light sensors. Here, why would you want to measure light? Everything is simple as, like, when do you turn your lights on and off, your outdoor lighting? Turn it on and off. You can make security sensors with light sensors. You can control the amount of light. Maybe an alarm for a dark room where you have some chemicals that can't be exposed to the light. So 3 types we're going to talk about. Photoresistors. So here's the schematic symbol of a photoresistor. Photodiodes. Here is a photodiode. 2 photodiode types. Schematic symbol for a photodiode. And then phototransistors. Okay, so there's a phototransistor there. It has a collector and an emitter, but it's missing its base. Its base current is provided by the light coming in. Here are the principles of operation. So for a photoresistor, the electrical resistance changes when that device's face is exposed to light. So this is a photoconductive device, right? The conductivity of that device changes based on the photons hitting it. And so you'll see these in light meters. You'll see these in like street light, daylight sensors. Night lights commonly use these because they're cheap. And also laser-based security systems I've seen use these. So for photodiodes, their principle of operation is different. The diode's reverse bias leakage current increases with the more light that you apply to the window. This is a photojunction device. This is more like a solar cell. The junction of that device is exposed through a window to light. And so applications here, you'll see smoke detectors, you'll see fiber optic links, optical communications, pulse oximeters. So, you can use photodiodes for communicating data. So instead of having a voltage go high and low, you can have a light intensity go high and low. And so this can be done over fiber optics, over glass fibers, or point to point over the air. And then you'll see these in pulse oximeters, which look through your finger and measure the light intensity of light on the other side of your finger. So phototransistors, they use, again, a different principle of operation. So there's light exposure to the junctions, and so that light exposure controls the flow of current through the transistor. It's a photojunction device, just like the photodiode, except you use them in a different way, which I'll show you. So these phototransistors are often used for optoisolators, object detectors, infrared receivers. So optoisolators, they're interesting devices. They're an integrated circuit where, let's suppose you're dealing with either maybe dangerously high voltages in one circuit, and then a low voltage control circuit. And you just don't want metal to touch metal, right? You don't want any kind of potential for a conductive path between a very high voltage and a control voltage that might be 5 volts. You can use these devices called optoisolators, which actually have a light emitter and a light detector. That detector is the phototransistor. And so the controller can illuminate the emitter and then be electrically separated from the detector and from what it's controlling that might have high voltages. Object detectors, you're using one of these in lab. This is the blade crossing sensor that you're using. And then in general, infrared receivers, like on televisions, anything that uses an IR remote control can use that. Okay, so these two have many applications in common, the photodiodes and phototransistors. We'll talk about response speeds, but the photodiodes are typically used for very fast response compared to the phototransistors, and they're a little slower. Okay, so what we'll do next time, we're going to walk through photoresistors, photodiodes, phototransistors, talk about how they work, but I think more importantly for you, how you would use each one of these and when you might use each one of these, so you can use these in your projects or measurements or research. Okay, so we will end it here. Have a great night.